Thanks, Doug. So as I have two goals in this talk today, first of all, I want to give you an overview of the Border Gateway Protocol and how it stitches together the different parts of the internet, the different networks that constitute the internet, and how different domains that have different economic incentives interact with one another. And the second piece, which is really the main part of the talk, is how the behavior of this protocol, in fact, its most basic property, does it converge or does it oscillate? Depends on the economic relationships between the different parties. And in fact, it's a nice example where everybody acting in a selfish manner makes the system stable. Okay, so that's sort of the punchline, that actually everybody acting in their own selfish interest is precisely the reason that internet routing is stable today. And this is joint work with Li-Shen Gao, who's at UMass Amherst. So I just want to give a little overview first about the internet. So the internet really is, as the name suggests, an interconnection of multiple networks. There are about 20,000 or so different so-called autonomous systems, which are basically routers and links run by one institution. It could be a large internet service provider like AT&T, it could be a campus like Purdue. And basically, the key point is it's an autonomously administered entity that controls the way those routers and links behave. And they could be large multinational ISPs all the way down to small campus networks. And the key point is that most traffic in the internet goes from one autonomous system to the other, potentially passing through 3 or 4 along the way. And so they have to coordinate at the places they interconnect. And that's where the Border Gateway Protocol comes in. They may be business competitors. They certainly aren't necessarily cooperating with one another, but they have to at least exchange some amount of information at the places they interconnect to make it possible for traffic to go from one end of the internet to the other. And that's where the economic issues get very interesting. So partially for scale reasons, they don't share their full internal topology information, and also because that information may even be viewed as proprietary. But they do have to do at least a modicum of interaction to be able to make inter-domain communication work. So this is a not uncommon way traffic flows through the internet, through maybe a half dozen or so of these different autonomous systems, starting from maybe a campus or a data center on one end, all the way to another campus or enterprise on the other, passing through potentially a regional provider up to a large national or multinational provider like AT&T or Sprint or UUNet. And these internet service providers may be richly connected to one another, sometimes in multiple locations. And the Border Gateway Protocol, BGP, that I'll talk more about, coordinates how routing takes place at this level of these clouds without much regard to what's going on inside the individual clouds. So for the purpose of this talk, you can think of an autonomous system as a node in a graph, and 2 nodes having an edge between them if they have 1 or more connections between them and they carry traffic on behalf of each other. So I'll be thinking about routing on this 20,000 node graph, even though there's actually immense structure and detail inside any one of these clouds. And the challenge with inter-domain routing is you could view it as one of the largest distributed systems we have in the world today. It's global in scope and has 20,000 or so nodes in it. And in fact, it's even more complicated than that. The routing is done at the level of blocks of IP addresses called prefixes, and there are about 150,000 to 200,000 of them currently. These correspond to different subnets in different networks all over the world. And routing has to compute paths to each of those from any point in the internet. There are around 20,000 or so autonomous systems, and that number keeps growing. And the number of paths and the number of routers is potentially in the millions. We don't even know, actually, in fact, how big it is, because each autonomous system is able to hide a lot of that detail about itself. And the most important thing, though, about BGP is not how big the internet is, but actually how flexible the protocol is. The network operators that run each of these different domains have incredible latitude to decide which paths they pick when there's more than one choice, and who they let use that path. And so what I mean is that the routing is not shortest paths. In fact, quite the contrary. Often the paths that are taken are not the shortest ones. They're the ones that are in the economic best interest of the party that's picking those paths. So they can pick whichever paths they want, and they can actually decide who gets to hear about those paths to decide whether they will let those neighbors of theirs use that path to reach those other destinations. So very flexible policy both for picking the paths and for deciding who else gets to use them. And that's what's going to be the key to the convergence problem I'm going to describe. The third issue is you really want it to converge fast. Right? A link fails on the internet or a node fails, you have a period of time where the routers are in disagreement about which way to forward traffic. And during that time, packets are going in loops, packets are falling on the floor, and things like voice over IP and video games are getting disrupted. Just to give you an example, at AT&T, people worried a lot about convergence because there were cases where tens of thousands of Halo players would die simultaneously during one of these convergence events. Okay, when you lose 20,000 video game players' lives at the same time, you definitely hear about it. So here, that issue is speed. How fast do the routers eventually get back to, in some sense, distributed consensus about where they're going to forward traffic? And in fact, that can take sometimes several minutes on the internet today. So it's orders of magnitude worse than we'd like it to be. I'm going to focus on a slightly different problem. Yeah?
Yeah, so one question that I have is convergence in this case really that critical, or is it simply finding a good path? So what I mean by that is you don't necessarily need the paths to converge in sort of the traditional Bellman-Ford-Dijkstra kind of algorithms converging, right, but rather as long as you find a path, which is good, that's good enough. Right?
Yeah, that's a really good point. So there's two things: how quickly do you converge, and what's happening while you're converging? And I think that the difficulty is while you're converging, the routers are in some disagreement with one another about which way to go, and so you have transient disruptions where each router is forwarding to the other, and so during that period, you might actually have.
So when you're defining convergence, you're really talking about a situation where loops could,
exactly,
in a sense, take place.
Where loops are black holes, if you will, where packets actually get dropped. But you raise an interesting point. There are routing protocols, some distance vector protocols that are provably loop-free while they're converging. Right. And in that environment, you're right. The transient paths you experience just might be less efficient than the final ones, but you wouldn't necessarily be losing packets. Right. But actually, in the particular protocol that BGP implements, actually you can have things like packet loss during the convergence process too. And so we're worried both about the speed of convergence and in fact whether the protocol converges at all. And in fact, that's really more the focus of the talk is, does the protocol even converge? Because if it oscillates indefinitely, you've got this problem basically never ending, where there's potentially routers in disagreement and packets being lost every time they repeatedly change their mind.
But if they were oscillating indefinitely, but oscillating over good paths, it wouldn't really matter.
Then it wouldn't really matter so much. I mean, it would matter from an engineering point of view in that you might not be using the network as efficiently as you could be, but you wouldn't have the stability problems of the data packets getting lost necessarily.
Even that may not be true depending on what you're converging to. Because you may
right.
be converging to something which may be suboptimal, like in the case of BGP.
That's true. That's true. Although potentially even more suboptimal when the routers are in disagreement about it. But you're right, the bigger issue here is that during the periods of disagreement, bad things are happening to the packets, which there are other protocols that don't have quite as bad of properties as BGP during that period, but either converging to the right path or avoiding the disruptions during convergence are really both the goal. And here I'm mostly concerned about the fact that the border gateway protocol actually isn't guaranteed to converge in the first place, where it may actually perpetually oscillate, and that I'm worried, particularly with this problem, although this other problem of how fast it happens also is quite important. So really the goal in this talk is to be able to guarantee that the global routing system of the internet will converge to a stable solution. And I'm going to argue, and I'll make this more sharp in the next few slides, that I want this to happen with purely local control. In other words, I don't want to create an oracle that's going to tell each of the different parts of the internet how to behave. I want to appeal to each domain, each AS, acting independently, and still making sure the system will converge. Because I want to be faithful to the fact that the internet really is a set of autonomous entities that can't be expected to coordinate with each other. Okay, so just to give you a sense of how the border gateway protocol works, it's really the glue that holds the parts of the internet together, and it operates at the level of destination prefixes or address blocks. So a domain like domain 1 might have a number of machines that all have addresses starting with 12.34.158, the first 24 bits being those values. And it will announce to its neighbor, hey, I can reach this block of addresses. And this domain has two choices to make. First, it must pick which route it wants. In this case, it's learned only one, so it picks it. And then it has to decide whether or not to tell its other neighbors about it. In this case, it does. It tells Autonomous System 3, hey, you can go through me to get to Autonomous System 1. And so BGP is, in that sense, a path vector protocol. Each domain receives messages from its neighbors, chooses one best route that it learns from one of its neighbors, adds itself to the path, and propagates it on. Okay, and that's important because each domain really only learns one thing from each of its neighbors, that neighbor's current best path. And it has huge latitude to decide which path to pick and whether to propagate it to its neighbors. So and then when any path that gets used, the data traffic will actually flow in the reverse direction of those messages. So here, AS2 might have learned a longer path that it preferred and would have been able to pick it. And it's not obliged to tell AS3 about this path. Right? AS3 and AS2 will only share that path information if they have a business agreement in advance that they'll pass that information along. Okay. So to talk about BGP a little bit more formally and without all this message passing detail, there's a nice formalism called the stable paths problem that Tim Griffin and Gordon Wolfong introduced a few years ago. So I want to explain BGP again in terms of that formalism. So here the nodes are autonomous systems, the edges between them are links, And here I'm listing all the paths that are permitted in this system. For whatever reason, Autonomous System 3 is only willing to tell its paths to Autonomous System 2 if it involves the path 3.0 and not when it involves the path, let's say, 3.1.0. And I've listed the paths in order of ranking, where for whatever reason, AS2 prefers the longer path through its clockwise neighbor over its direct shorter path. Maybe this path is higher bandwidth, maybe it makes more money going that way. For whatever reason, it prefers that longer path over the shorter one. And I'm going to set up an oscillation here. So the game that BGP plays is every neighbor picks the highest ranked path out of the paths that its neighbors picked, because those are the only ones it actually learns at any given time. So 2 cannot pick the path 2.3.0 unless 3 is simultaneously picking the path 3.0. Okay, so starting the game at the beginning, Autonomous System 1 only knows its own direct path and it picks it. Okay, so it picks its second favorite path 1.0. Well, this makes Autonomous System 3 really happy because now it learns the path 1.0 and picks its favorite path 3.1.0. AS2 is not so happy because it never learns the path 3.0 and is forced to pick its second best choice, 2.0. Problem now is AS1 is happy because its favorite path is now available, because now it has the option of picking the path 1.2.0 that it likes more, meaning that AS3 no longer has the option of taking 3.1.0, forcing it to go on 3.0. Well, that makes AS2 very happy. I've got an hour, right? I can keep doing this. Anyway, this goes on and on. And eventually we get back to the beginning, and this will repeat indefinitely. So this is called in the Griffin and Wolfong paper a bad gadget for autonomous systems that will perpetually oscillate because the preferences of these 3 domains around the periphery are inconsistent with one another, and there's no stable solution. And so our goal is to make sure these kind of situations can't happen and to come up with conditions under which they won't happen. So before I go on, any questions about the stable paths model? So when I heard the Griffin and Wolfong talk at SIGCOMM a few years ago, the first thing I wondered was, would this ever happen? Right? Why is it that every domain here doesn't like its own direct path to Autonomous System 0? And it seemed to me that this would never happen in practice. And in fact, what we found in the work that I'm about to describe is, in fact, it wouldn't happen in practice. This doesn't make any business sense, what I just described here. And that's going to be the punchline of the talk, is it doesn't make sense. Nobody here seems to own the responsibility for being the service provider for AS0. And that's the reason everybody seems to prefer somebody else's path over their own, and that doesn't really make business sense. And I'll formalize what I mean by not making business sense, but the key punchline here is situations like this really don't happen in practice because each of the domains have economic incentives, and those incentives drive how they rank these paths and which paths they expose to their neighbors. And we'll show how this kind of situation goes away when you think of it that way. So the first thing that Griffin and Wolfong proposed when they did this work was, okay, well, what if we had a global registry? Everybody published their part of the topology, and everybody said what routes they pick and what routes they're willing to tell others about. What would happen? Well, so the idea would be you create a registry, you make every autonomous system publish everything, and then you check for conflicts, and then you find some way to resolve the conflicts you have so that the system doesn't oscillate. And there are many, many, many things broken with this. The first one being just keeping such a registry up to date be very difficult. The second being that autonomous systems have business reasons they don't want to share that information. They don't want to say who their neighbors are. They don't want to say which routes they prefer, because that reveals something about their business relationships that they don't want to share. And finally, this is really the death blow. Even if everybody participated, and even if the registry was accurate, the problem of checking for convergence problems is NP-hard, or NP-complete. And it's even worse than that. Even if you knew a system was stable, there was a unique and stable solution, as soon as you delete an edge or delete a node, you've got to repeat that check again. There's no guarantee that the system, after you remove edges or nodes, remains stable after you do that. Okay, so basically the idea of having a global oracle to check for these things is really a non-starter for a variety of both practical and theoretical reasons. So we really want a solution that doesn't require this level of cooperation between domains. So really what we want is the ability of each domain to be able to act locally and still achieve the global properties we want. And the global property we want is provable convergence. So we want flexibility. We want still to preserve, at least in part, the ability of each AS to pick its policies, because that's really what BGP is all about each domain having some say over what paths it picks. We don't want them to have to publish information that would be viewed as proprietary. We don't want to change BGP because you'd have to reboot the internet. And that might be really useful, but it's actually kind of hard. We'd like provable convergence, even if we were to delete nodes and edges. We want to know that the system will always be stable. And the way we're going to achieve this is to make 3 assumptions about the topology of the internet and the rules that the different autonomous systems apply in picking paths. And the key point here is that these assumptions are a pretty accurate reflection of reality, and that's why the whole thing works. So the first is going to be assumptions about when you have more than one path, which one do you pick? Do you pick the shorter one? Do you pick the one through a particular kind of neighbor? The second are export policies. Once I pick a path, who am I willing to tell about it? And the third one is more fundamentally about the structure of the autonomous system graph and who connects to who. Okay, so really in the internet, there are 2 primary business relationships that the domains have with one another. They're either customer-provider or peer-peer relationships. So I want to walk just real briefly through those 2 relationships because they're a big part of how we make all this work. So customer-provider relationship is a relationship Princeton has with AT&T, my current employer with my former employer. Princeton wants AT&T to provide reachability to the internet. That means 2 things. Princeton needs AT&T to make sure the rest of the internet can reach Princeton, and that Princeton can reach the rest of the internet. And so in doing that, 2 things happen. When Princeton has a destination connected to the internet, and it tells AT&T about it, AT&T has to tell all of its other neighbors, no matter what business relationship AT&T has with them, so that those other domains learn how to reach Princeton, because Princeton's depending on AT&T to make sure traffic comes in the reverse direction to Princeton. And that's what Princeton's paying for. Now, if AT&T knows how to reach a destination in the global internet and it tells Princeton about it, Princeton agrees to tell only its own downstream customers, not any other providers. In other words, Princeton is not providing transit service for AT&T. AT&T and Sprint do not communicate via Princeton. Okay, so here's the first assumption I'm making, which is that when a provider tells a customer how to get somewhere, that customer doesn't tell other providers about it, but only its own downstream customers. Now, you may be wondering, does Princeton have any downstream customers? And it may surprise you, actually, that it does, including at the Princeton Public Library, the Princeton Regional Schools, and so on. So all of those smaller parts of the internet below Princeton get to learn from Princeton how to reach those destinations, but not other large ISPs. Okay, so that's the first assumption. And this is really all built up around the fact that Princeton is paying AT&T for this service. AT&T is not paying Princeton for the privilege of using it to reach other parts of the internet. The second relationship is a peer-peer relationship. It's a kind of relationship AT&T and Sprint have, which is they connect to each other free of charge because each of them get mutual benefit from doing so. And the mutual benefit they get is that each of them can now reach each other's customers. So this kind of relationship exists between all the so-called Tier 1 ISPs. They don't have providers of their own, so they have no way to reach each other's customers if they don't connect directly. Okay, and so they do. So a destination, let's say at one peer, he would learn from his customers how to reach D, and he would tell his peer as promised to his customer, and his peer will tell only his own downstream customers, not other peers or other providers. Because this link exists free of charge just to carry traffic between their respective customers. It doesn't exist to carry other traffic. So these peer-peer links are special in that the exporting of information about them is restricted to parties downstream in the hierarchy, if you will. Right? In other words, Sprint would not tell UUNet about that link. Another example, Princeton has a peering link with the local cable company in town. They connect to each other free of charge because traffic goes from people who live in the town to the Princeton campus, like faculty and staff who live in the town. That link is there because they pay less money if they have that link than if each of them had to send that traffic up through a service provider. But that link isn't meant to be used to reach other parts of the internet. Okay, so these peer-peer links are needed both for basic reachability at the top of the internet, if you will, between large ISPs, and also exist in lower levels of the hierarchy to connect people that for financial reasons find it advantageous to connect directly rather than send their traffic up through a service provider. Okay, so here's my second assumption, that a route learned from a peer won't get advertised to other peers or to upstream providers. Okay, so the second assumption I'm making about the exporting of routes. Any question about those? Yeah. That's a great question. So these assumptions are really common business practice and make economic sense, but there's nothing in BGP that enforces them. So in fact, there is a tenuous leg all of this work stands on, which is that everybody obeys common business practice, both because it's in their financial best interest and because it makes the internet stable. But the protocol itself doesn't preclude people from shooting themselves in the foot. Yeah, good question. Any other questions? Okay. So The next assumption that I want to make is about the structure of the graph. Okay, so the assumption I want to make here is that the provider-customer relationship is indeed hierarchical. My customer's customer is not my provider, in the sense that Princeton is a customer of AT&T, Princeton Regional High School is a customer of Princeton, but Princeton Regional High School is not a provider of AT&T. In other words, we don't expect edges like this to exist where somebody near the bottom of a chain of provider-customer relationships can't somehow appear back at the top. Okay, in other words, provider-customer relationships are acyclic. Okay? And that's consistent, again, with the fact that provider-customer relationships relate to size and scope and the exchange of money. So it doesn't make sense for a really small party that, in fact, needs its own providers to get someplace will somehow be a provider for a much larger autonomous system. Okay, and then the third assumption I want to make is about the ranking of paths. If I learn more than one path to the same destination, which one do I pick? And so what I want to do is classify these paths in terms of who I learned them from. Who is my immediate neighbor? Did I learn it from one of my own customers? Did I learn it from one of my peers? Or did I learn it from one of my providers? And what we want to do is say that, hey, a service provider would prefer to send traffic through his own customer rather than through one of those links to a peer or one of those links to an upstream provider. Now, in doing that, I'm not restricting how a provider might distinguish between multiple different customers. It might pick one customer over another. It might pick the shorter path. It might not. But that it wouldn't prefer a route through a peer or a provider over one through a customer. And the reason that makes sense is that customers pay for service. So service providers get revenue by sending traffic on the links through their customers. At best, they're neutral when they send traffic through a peer. And in fact, there are cases where imbalance in a peering relationship, where I need you more than you need me, can cause peers to renegotiate the terms of their business agreement. So in fact, I have a very strong incentive not to use those links when I don't have to, because otherwise I may start to be on the lower end of the stick in that business relationship. And finally, I wouldn't want to use a path through my provider because I have to pay at that point. So for financial reasons, often the first thing that providers look at when they're picking amongst a set of routes is to pick the revenue-generating route over the non-revenue-generating route. And so that's the reason we think this assumption is reasonable. Amongst customer routes, pick any one you want. If there is no customer route, pick any of the routes you learn from any peer or any provider. We're not restricting that at all. Okay, and that's the third assumption. So we have restrictions on who can tell what to whom, restrictions on the structure of the graph, and finally restrictions on which route you pick if there's more than one choice. Yeah?
Does this assumption imply that two top-level providers cannot communicate to a third top-level provider?
That's true. That's right. So for example, AT&T doesn't communicate with UUNet through Sprint.
Does every pair have to be paired?
Exactly. Yeah, that's a really good point. So a consequence of that is that the top of the internet is a clique of peering edges between tier 1 providers, where tier 1 provider means providers who have no provider of their own. And they have to have a clique, otherwise parts of the internet are disconnected from one another. An interesting consequence of that is that when people argue about these peering relationships, when they think the balance of power is not even, that often means that they snip that link, they play chicken. And there have been a few high-profile examples of this where two tier 1 ISPs argue over whether their relationship really should be peer-peer or if one should be the customer of the other. And when neither side gives in, that link gets cut and parts of the internet are partitioned. Right? Which is interesting because the graph is by no means partitioned. Right? The graph is much, much more richly connected than these business policies would suggest. But the business policies are explicitly restricting which edges can be used, so that the graph is actually more fragile than it might seem. Any other question about that? Okay, so those are the three assumptions. And I just want to really briefly walk through the argument for why this is enough to make the problem I described earlier go away. And the basic argument I want to make is that with these three assumptions, the routing system is guaranteed to converge to a unique and stable solution. Now, unique may or may not be viewed as important. Unique is useful just because for predictability of where the traffic is going to go, it's kind of nice that the system converges to one answer. But the main important thing here is that it's a stable solution so that the system won't oscillate. So I'm going to walk really briefly through the proof for a couple reasons. One is just to give you a sense of why the result is true. And the second is I want to also illustrate that this is a constructive proof. And that's important because it can be used to predict what routes different parties will pick. And I'll come back to later in the talk why that's actually a nice feature of the proof. So the basic idea of the proof is that at any given time, the system state is the current best route that any domain is currently picking to reach that destination. And I'll focus just on one destination in the proof. And I'm going to activate the domains, activate the nodes. And whenever I activate a node, it's going to look at the choices its neighbors are currently making, pick its own best route from that set. And I'm going to activate the sequences, activate the ASs one after another. And so I'm going to first demonstrate that there is a stable state, that there is some order in which I can wake up or activate these nodes such that they lead to a stable state. And then the argument that the system converges is that that ordering I'm going to show you is embedded in any real ordering that the messages actually have. In other words, in reality, BGP is asynchronous. Nodes are waking up and making decisions at random times. But eventually, the node that's first in my activation sequence will pick a route. And once it does, it'll never change its mind. And then eventually, the second node that I have in my sequence will be what will make a decision, and it'll never change its mind. So I'm going to show you a sequence one at a time where each node is activated once, makes up its mind, and never changes it. Although in reality, there'll be a little bit of message passing that goes on for a while before this stable activation sequence manifests itself. Okay, so just to make the argument for the proof, it really proceeds in two parts, and it relates a lot to my point that the customer-provider relationship is acyclic. So I'm going to start from the destination and go up the customer-provider hierarchy and make decisions in an order that's consistent with that hierarchy. In other words, AS1 and AS2, who are both providers of this destination, can make their decisions right away. There's no harm because each of them prefer a route learned through a customer, and they have a route from a customer. Nothing they learn later from any other part of the graph will ever change their mind, because they'll never learn another route that's through a customer, and routes through peers and providers won't be as preferred. Okay. Now, once they've both picked their routes, their provider, AS3, has routes learned from all of its customers and can safely pick a route learned from a customer. Nothing it learns later will make it change its mind. Now, none of the other nodes are able to make a decision at this point. Only percolating up the hierarchy has taken place now. And now what I'm going to do is flip things over, have everybody tell their neighbors the choice they made, and now walk down the hierarchy in the other direction. So basically now, starting at the top, I'll look at the first node that doesn't have any parents that have not yet made a decision. It'll make a decision, percolate down to its children, and so on. So in the reverse direction, we percolate down from the top of the internet hierarchy down to the leaves. The key point being now that every node that's left will be picking a route learned from one of its peers or one of its providers. So I don't have to worry about it learning something later that will cause it to change its mind. Okay, so that's the basic argument, that you're going to percolate up the provider-customer graph and then down the provider-customer graph. And eventually all the autonomous systems will have made a choice. And they'll make a choice that they'll never change. Okay, so that's sort of a high-level sketch of the proof. In the paper, we go into a lot more detail about why that holds. But the key point here is I used all three of my assumptions. I used the DAG, the fact that this is an acyclic graph, to construct this ordering. I used prefer customer, in fact, to make it clear that everybody can pick a route as soon as all of their customers have made a choice. And finally, I used the restricted export restrictions to know that there's no chance people will learn things later through some indirect chain of provider or peer kinds of edges. Okay, so why does this work? Or does this actually work? So I think that there's really, yeah.
So is this also a necessary set of conditions for convergence to occur?
Oh, that's a great question. So the question is this a necessary set of conditions? No, it's just sufficient. I've not yet found an example where I can relax the constraints, but the proofs are only showing it's a sufficient condition.
I see.
Yeah, in fact, all of the positive results for BGP convergence have just been sufficient conditions. So there's still a lot of argument about the boundary between the necessary and sufficient conditions. And there's been some recent work I'll talk about in a few slides about trying to relax some of the assumptions we presented. And invariably what happens is whenever you relax one of those three assumptions, you get a negative result. And then you have to tighten it by strengthening one of the other two assumptions, which is not a proof that this is a necessary condition, but it's suggestive that we're lying pretty close to the boundary of what you can and can't do.
Is there some assumption that these links don't change, or that I don't change my peering relationship?
Ah, great question. What happens if I change?
Yeah.
So that's interesting. So using the same insight, we can say when two parties are going to change their business relationship, what order the two ends of the link should make the change. Because there's some cases where one of them going first will actually make the system vulnerable to oscillation. To be honest, it's only in the extreme case where customer and provider swap, which I doubt that's going to happen, like Princeton becoming AT&T's provider. But we can show that if that's done in the wrong order, where one guy configures his routers first and the other second, that during the transition period there can be oscillation. So we can say who should go first. Although to be honest, practically speaking, I don't think Princeton and AT&T are going to. I mean, it sounds good to me, but I don't think they're going to swap their business relationship. Yeah, good question. Any other questions? So what's the right way to interpret this result? I think there are two ways to interpret what I've just been saying the past few minutes. One is, well, yeah, this is just descriptive. This is explaining why the internet doesn't oscillate. In other words, people do already follow the guidelines, assumptions, rules, whatever you want to call it, that I proposed, because they are consistent with their own economic incentives. And there are a couple of things that suggest that that's true. First of all, that the assumptions I made were very, very consistent with business incentives and best common practices that are documented in sort of operator forums. The second, that's looking at measurement data. So we looked at measurements of the Border Gateway Protocol. There are a number of public domain repositories of the messages exchanged in the Border Gateway Protocol, and there are millions of messages a day. So that does suggest a system going through churn. Is any of that churn oscillation? Okay, so what we did is we looked at, first of all, popular destinations. Amazon, Yahoo, CNN, you know, the top 20 or 30 websites and all the destination prefixes that correspond to them. And we found that they're stable in BGP for weeks at a time. On average, there's not a single message concerning any of those destinations for 10 days at a time. Okay, so that's suggestive those destinations are not oscillating, because if they were oscillating, we'd be seeing messages a lot more frequently. Now, what about where are all these millions of messages coming from? The vast majority of those messages concern a small number of extremely unstable destinations, some of which having routing changes every 45 seconds. Okay, so maybe they're oscillating. But in fact, if you look at the messages in more detail, they're oscillating between being completely unreachable and then being reachable, and then being unreachable again for a long period of time. So it's suggestive of flaky equipment or failures at the periphery of the internet, where these destinations connect over an unstable link that goes down and eventually comes back up, as opposed to there being a policy oscillation in the protocol itself. So this is still bad, because the system is unstable. But first of all, it only affects destinations that receive very little traffic. And in fact, it appears to be caused by equipment failure, not by policy oscillation. Okay, now this is by no means a proof, but it's certainly consistent with our observation that the system shouldn't be oscillating if people are obeying their business incentives. Okay, so a second way to look at this, and it relates to the question he just asked me a moment ago, is you could view these as guidelines, as rules of how people should behave when they configure their routers so that the system has good global stability. Because there's nothing in BGP itself that forces anything I said. Right? Everything I said was just a best common practice or an assumption or a guideline or a rule, but people can either intentionally or unintentionally violate those assumptions when they configure their routers. And so we could argue that these are guidelines, that people should be trying to, for the greater good and for their own economic reasons, be obeying these guidelines and verifying, in fact, that they've correctly configured their networks. Okay, that's all well and good, but my assumption about the business relationships was admittedly a little simplistic. I talked about there being only two types of relationships, and under no circumstances would anyone want to violate the assumptions I outlined. And that's not quite fair. And in fact, I'll outline a case in a moment where somebody might want to view the relationships a little differently, and I'll show how we can make the results extend to that case. So in particular, we looked a lot at playing off one condition against another. We made three assumptions, and there are a whole bunch of different assumptions we could have made about the ranking of paths, about the exporting of paths, and about the graph. And so we thought, well, gee, some people might want to route through their peer instead of their customer, if even though they don't get revenue when they send traffic through their peer, because maybe their peer has better performance, maybe there's congestion on the link they have to their customer. So what if we added a little bit of flexibility, that you could pick a peer route over a customer route when they're the same length, rather than forcing the customer route to be picked even when the peer route is shorter. In other words, I'm still requiring that I never pick a route through a peer that's longer than a route through a customer, but I am willing to pick the peer route over a longer customer route. So if we relax that assumption, we can show the system can oscillate. Okay, so it relates to your question about sufficient conditions. We make that small change, and we can show examples now where the system will oscillate. But if we add an additional assumption about the structure of the graph, not only is the provider-customer relationship required to be acyclic, but now even if there are peer edges mixed in there, they also we can't have a cycle of this type. So in other words, there can't be any cycles that consist of provider-customer and peer edges in them like this. And then we can show again that the system will converge and be stable. And the beat goes on over and over again. We relax one assumption, we find a counterexample where the system oscillates, we tighten another assumption, and things are fine. So it's suggestive that these three assumptions play off against one another in interesting ways. And in fact, there's a space of different assumptions that can be made with that all assure that the system will be stable. Okay. What about backup relationships? That's something I ignored in the first part of the talk, but they happen in practice quite a lot. You know, maybe Princeton connects to AT&T as a primary provider and another provider as a backup, where it really intends the backup provider to go indirectly around through the other provider. In other words, a backup provider isn't supposed to pick the direct link to you. It's supposed to actually go the other way around. In the example here, another example, this exists between Harvard and Harvard Business School, just to make the example concrete. Harvard has one service provider, Harvard Business School, another autonomous system, has a different service provider. They have a peering edge, so traffic between the two of them stays on campus. And in fact, they make it such that either one of them can survive the failure of its ability to reach its upstream provider by using the other. So under failure scenarios, Harvard's allowed to go to Harvard Business School to get to Sprint, rather than depending on its connection to AT&T. Now that violates one of my assumptions, right? It violates the assumption that a peer never tells upstream guys about routes he learned from his peers. Okay, so we can find that that will oscillate. Now what's interesting about that is people add backup paths into the system to make it more robust. And ironically, what we find is it makes it more susceptible to oscillation, which makes the system behave badly. So it's kind of an interesting result that attempts to make the system robust compromise stability. So what we found is, again, if we extend the results a bit, that we can make this work, which is if we keep a counter on every route of the number of backup links in the path. In other words, whenever that routing information traverses a link that's a backup, if we increment a counter and carry that counter with the message, and always prefer paths with fewer backup links over ones with more, then again the results hold. So a generalization is you can have these more liberal export rules as long as you keep track of how many times you violated them, right? And then pick paths that violate them less often. And then we can show, in fact, that the system is stable again. Okay. Any question about that? Okay. So more complex scenarios, some related to what Sanjay said. We can have more complex relationships. Relationships really can differ between two domains. These relationships might not exist for all destinations. For example, some ISPs in Europe are customers of large ISPs in the US when it comes to reaching destinations in the US, but they may be peers in Europe. So depending on which part of the internet they're trying to reach, their business relationship is different. No problem, because these guidelines are really on a per destination basis. Each destination's routes are picked separately. Similarly, if two ASs have both a backup relationship and a peer relationship, we can make that work. And if two ISPs are providing transit service between a peer for each other, under restricted circumstances, we can tolerate that. And finally, we can tolerate cases where ASs change the nature of their business relationship, particularly if it's done carefully to happen in the right order, so that during the transition we don't sacrifice stability either. So just to conclude, and I just after this have one slide on more recent follow-on work that's taken place. The basic idea here is we want to avoid oscillation in the routing system. Make three assumptions: that the relationship between the different providers and customers is hierarchical, that you export routes based on your business relationship. In other words, customers don't tell other providers about the routes they learned from one provider, and that they pick paths based on those relationships. That you pick revenue-generating paths over neutral paths, or ones that cost you money. And the nice thing about it is this doesn't require any global coordination. Each domain obeying these assumptions independently, and it's suggestive, in fact, that they already do this, is enough to make the system stable. In fact, you could argue the system is stable precisely because these conditions hold. It doesn't require any change to BGP. You don't have to reboot the internet. The system's guaranteed to converge, even if links fail and the graph changes. As long as the assumptions that I made are still true, the system is still guaranteed to converge. And most importantly, these guidelines are consistent with the business incentives of the different domains. So I want to talk a few minutes about more recent work in the last year or two that's followed up on this, because it's kind of interesting. The first is other people have been tussling with this question of what is the space of necessary and sufficient conditions for guaranteeing convergence. So there's been some nice work on algebraic frameworks for coming up with policy languages for BGP. And a really interesting paper at last year's SIGCOMM on fundamental limits. So these researchers decided, well, gee, what if I want to export routes to whoever I want? Every domain should be able to decide who they tell about the paths. They found if they did that, if they completely relaxed that assumption, they have to do shortest path routing. Okay, this is a very, very strong negative result. If I give every autonomous system complete autonomy in who they export routes to, everybody's forced to do shortest path routing if you want to assure that the system doesn't oscillate. Okay, so that means if you basically relax one of those assumptions of those three completely, you're stuck with the most conservative assumptions for which paths can actually get picked. Okay. A second thing is I talked about routing as if each autonomous system were a single node, a single router. But in practice, autonomous systems have dozens or even hundreds or thousands of routers in them. And in fact, BGP is spoken inside each of those networks too, or at least inside large ISP networks, for those routers to share the information they've learned about the outside world. As a result, internal BGP can oscillate. And in fact, this is a case where oscillation has happened, where depending on how internal BGP is configured, you can have persistent oscillation inside a single domain in that little miniature routing system. And so this work was extended to this case to be able to come up with conditions that for operators to design their internal BGP configuration to avoid having the system oscillate. And separately, the fact that the proof that I outlined earlier is a constructive one is important, because inside a domain, the operators have all the information. They know the topology, they know all the routing information. And so this constructive proof I presented earlier becomes now an algorithm for saying what answer will the routers pick based on how they're configured. And this is embodied inside AT&T in tools for traffic engineering. The operators want to know what's going to happen, where's the traffic going to go. They use that same algorithm that I showed in the proof to determine where the traffic will actually go. Another interesting thread of work is these business relationships. I mentioned these domains have routing policies that are based on their economic incentives, which are based on their business relationships. But you can invert that way of thinking completely and say, hey, if I know what paths I see in the internet, maybe I can infer what business relationships people have. Okay, simple example, if you see a path 1, 2, 3, you know that 2 is willing to let 1 go through it to get to 3. Right? So it's suggestive that 1 and 2 and 2 and 3 have only certain kinds of business relationships. Not possible for 2, for example, to be the customer of both 1 and 3, because 2 should not be letting 1 go through it to get to 3 if that's the kind of relationship they have. So if you look at lots of paths on the internet that are seen in public data, every triple of nodes that appear in a row impose a set of constraints on what policies could have been applied that would let that triple appear. And what's nice about that is if you combine enough of those together, you can infer who has what business relationship with whom. You can figure out who pays whom for internet connectivity. And so there have been a number of studies that do that in order to get business intelligence about the business relationships in the internet. And also to characterize how the AS level topology has grown and evolved over time. And finally, knowing these business relationships actually has a lot of competitive value in that you can decide, well, gee, I'm treating you as a peer, but one of my competitors is treating you as a customer. Well, maybe I should renegotiate my business relationship with you because maybe this is not in my best interest. And knowing the business relationships that other people have is helpful for that. And finally, if people misconfigure their routers, if they announce routes that are violating the assumptions I mentioned, this becomes a way to detect that those routes look funny, that they violate, in fact, the business relationships you thought those parties had with one another. And it becomes a way to detect routes that are suspicious that might need to be filtered to avoid having the routing system be insecure. Okay. So any questions? Yeah.
So Jennifer, this talk seems to be fairly like a positive certificate to BGP, right?
Right.
But it seems, but there have been people talking even last year about redesigning BGP from scratch. I think there's a proposal, it's called HLP, and, and people have been talking a lot of problems with BGP and so on. So is this, could you sort of position this work?
That's a great question. So this paper, this talk suggests BGP is good.
Yeah.
And in fact,
is that the common wisdom?
Yeah, no, it's not the common wisdom, and I don't even agree with it, so I shouldn't have given that impression. Yeah, so first of all, I think a question that was raised earlier is really key. This stuff works, but it works only because people correctly configure their routers. So there's nothing intrinsic about BGP that makes this hold. It's really everybody acting correctly in their selfish interests that make it work. So if people mess up, all bets are off. So I think that's the stability result is fairly dependent on the business relationship. I think a second thing is it's not obvious that these particular business relationships are the most natural. I mean, it kind of makes sense that you'd have customer provider, and peer-peer kind of makes sense to provide the connectivity that's otherwise lacking, but it's not obvious why there can't be things a little in between, where maybe I pay you a little bit of money and you let me use some extra routes. There could be much more fluidity in these business models than what I described. There doesn't appear to be much of that today, but there's nothing, again, intrinsic about the system that guarantees these business relationships are natural. And I think a bigger problem is it's not at all obvious that the routes that have been picked here are efficient. Right, and it goes back to the question you asked at the very first slide, actually. These routes are stable, but they may not be efficient. Like, maybe it makes sense for AT&T to go through Sprint to get to UUNet, but that path doesn't manifest itself because people are doing their routing based on these bilateral business agreements. And so the resulting system may not actually be that efficient.
So you think that ideally the system should work, but maybe configuration errors and so on are one of the big reasons why things don't quite work as well?
Yeah, certainly configuration errors are part of it, but I think intrinsically when things are done bilaterally, there are missed opportunities to take advantage of more of the path diversity. I mean, another problem is BGP is a single path protocol, often one path, and there's no performance information or reservation information passed along with it, so you don't have any idea if the paths you learned are satisfying your needs. And if there might have been other paths that could have been exposed to you that do satisfy your needs, that's all not in there as well. And I think finally, at the very beginning, I mentioned the speed of convergence. Actually, we have some new results we're working on where if people obey these business relationships, how fast will the system converge? And there's some positive results there, but also some negative ones, that even if you obey these guidelines, the speed of convergence may actually still be quite bad, unless you make even tighter assumptions than what I made here.
And how bad is quite bad?
Oh, exponential. Yeah, I guess that's pretty bad. Maybe I understated that a little. Yeah, it's really bad. Now, whether, again, that happens in practice is hard to say because the diameter of the internet isn't so big. It's 6 or 7 hops. But there are some negative results, even when these assumptions hold, if what you care about is how fast the convergence happens. Yeah. Other questions? Yeah.
Do you have any feel for how much administrator error would really take to set some dangerous oscillations in place?
That's a great question. It's hard to say because it's certainly the case that any one domain misbehaving has the potential to set up an oscillation. And there have been cases in internal BGP of a single configuration error causing the internal system to oscillate. So I think that in that sense, there is a fair amount of vulnerability to single configuration errors. Now, on the flip side, if you say, well, gee, how often do I add a new peer or add a new customer and really touch that part of the config? Maybe not so much. So in that sense, maybe it's not something that's going to be happening on a daily basis. But it's certainly, configuring BGP is quite complicated, and a lot of it is done manually today. So it's certainly, there's plenty of scope to screw up. Yeah, good question. Yeah.
There's an economist by the name of Hyman Minsky who has proved formally that stability is destabilizing in the sense that when you have large numbers of players who are acting according to their own economic self-interest, that long periods of stability set the stage for a spectacular bust.
Okay.
And I wonder if there's something in the model of Minsky that does not apply in your situation, or it would be quite intriguing if actually it does apply, in which case there could be something quite scary that would happen at some point.
Oh, that's interesting. I'm not familiar enough with his work to know.
His proof is something like this, that when you have stability, people expect it and act on it.
Ah, okay.
Their behavior changes based on the expectation of stability, which destroys stability down the road. It might take a long time, but
interesting.
What he proves is that it will eventually happen.
Oh, that's interesting.
It's something that might be interesting to look at.
Yeah, I'll take a look at that.
I hope that the model, there's something in his model that doesn't quite apply here.
Right, right.
Because otherwise, well, you should all be scared.
Right.
But I think in Jen's case, because of the assumptions, she has, the expectation is not from the players of the game. The expectation is not that stability is natural, right? They are in a certain sense following this business rule, and therefore, I think what probably in her case is happening is that the system is converging to some kind of a Nash equilibrium.
Right.
Right. So which might be stable.
The backup gives me pause. The backup gives me pause. I mean, it's just like what people do to prepare for something bad happening. They make contingency plans that when something bad does happen, their contingency plans collectively defeat each other. This is what would happen in Unity.
Right.
Right.
I thought that you had a solution for the backup.
So we do, but it's not commonly applied. So I think, that point's well taken. We basically showed that common practice for doing backups is risky in that sense, and getting people to agree. I mean, we required at least some amount of global coordination there to maintain that counter of the number of backup edges in the path. So it's certainly technically feasible to implement what we described, but it's not something that's done currently. So you're right in that sense. Certain types of failure scenarios might manifest those.
The recipe of Minsky for avoiding this is some moderate amount of central coordination. very judicious amount of central coordination. That was his recipe for avoiding crises.
So I think one difficulty here is figuring out who that party would be in the context of the global internet.
In his case, his view was that government should provide that.
Right. Then which government? Yeah.
Kind of related. You made the point that some of these business models you didn't think were entirely natural or the exclusive. To what extent do you think the business models may have developed because those were the ones that succeeded in stability given the protocol?
That's a good question. I don't know.
As in small, as in groups that tried other business models,
failed,
had stability problems and failed.
Yeah, my guess is, that's a good question. My guess is not, just because I don't think there's been evidence yet that there have been stability problems. I think you're right. If there were sort of a large conglomerate of ASs that decided to do things completely differently, they might encounter such stability problems. But I don't think we had that diversification of ideas coexisting long enough to be able to make that happen. So my guess is that probably didn't happen. But rather that I think these business models are simple, and I think bilateral business relationships are a lot easier for people to sign up for. And it is interesting, actually, in the US, the extreme notion that peers are settlement free, they don't pay each other money, that's a US thing. In Europe, actually, it's a little bit more murky, in that there can be it's still a peer-peer relationship, but it might be that one party pays the other just a little bit because there's a perception of an imbalance of power. And so that doesn't change the policies that they end up applying, but the way they translate it into the exchange of money is actually slightly different. And it kind of makes sense that might be a little more murky. It's not clear why you and I should terminate a connection between us just because I get a little more out of it than you. It might make more sense that you pay me a little, or I pay you a little. I mean, yeah, good question. Yeah?
I got a question. Since BGP is kind of easy to mess up,
Mm-hmm.
you can do like black holes or whatever. Do you see something else coming in its place in the near future? Because like a lot of effort was being spent on SBGP type things.
That's a great question. So SBGP is secure BGP, which has been worked on for almost a decade now as a secure replacement for BGP that authenticates the messages sent by the various parties. And it's so far not been deployed for a number of reasons. One being that it requires global deployment, a reboot the internet, Flag Day. Requires a public key infrastructure, which has many of the same problems of who's going to run that. And I think the Department of Homeland Security would very much like to, but their offer was rejected by many people. And it also involves crypto overhead on the routers. But I think actually the question of how to incrementally deploy new things into BGP is actually quite interesting one, because so far we've been fairly bad at adding extensions to BGP that are clean in any way, precisely because they need global cooperation. So one thing I'm particularly interested in is, instead of having the routers speak BGP, having a small collection of servers in each domain take responsibility of being the global actors in the inter-domain routing space and speak to the other domains, and potentially allow those nodes to run new code while still speaking to the legacy routers using the conventional BGP. And that might have the advantage of taking the overhead of doing some of the crypto operations for SBGP and having a place to run it when the legacy routers already bought and in the field don't support it. But maybe we don't really need routing to be quite so distributed that every router is running it. And my hope is that there are incentives for one domain to deploy such a set of servers for better security, better performance. And then when other domains start to do it as well, they have an incentive to run a more secure variant of the protocol on the sessions they have between those boxes. So I think there are potentially ways to get out, but it requires backing away from BGP in baby steps because of this difficulty of not being able to do a reboot. Yeah, good question. Yeah?
Is there anything that designers of distributed systems or overlay networks can learn from this result in order to design their own application-level routing infrastructure?
That's a really good point. So I think certainly other routing systems might very well have the same kind of properties, and there also have been people proposing using BGP for things like IP telephony, not to do global routing, but to exchange information amongst VoIP servers. And so I think when other distributed services think of either using BGP directly or using path vector protocols where there's policy in general, I think then these kind of problems certainly exist there. And it's not easy to figure out how to constrain the system to have flexibility and not have oscillation problems. I think that's a pretty general issue that could happen in overlays as well. Yeah. Other questions? Great, thank you.